This video is just an introduction to 3J and 4J coupling, which will be needed for the NMR workshop that you will be doing. So what is coupling? Well, before we talk about that, it's probably a good idea to remind yourself that when we're looking at an NMR spectrum, we are actually looking at a frequency output that has been converted to a chemical shift. So when we record an NMR spectrum, we always add a reference sample, and in this case I'm just highlighting that we use tetramethylsilane. So over here is the structure of tetramethylsilane. It has 4 methyl groups plus a silane. Now the chemical shift of this has been given 0 parts per million, or a chemical shift of 0. So why is that important? Well, what we need to do is we need to think about the relationship between chemical shift, the operating frequency of the NMR spectrometer, and also the sample frequency. So when we actually think about that in terms of mathematical equation, we have this relationship that is shown here. So we have an example here. If we're thinking about a compound that gives a signal, and we'll say just for simplicity that that is a singlet at 54 Hertz, and it's recorded on a spectrometer that has an operating frequency of 60 megahertz, then this singlet will resonate at 0.9 parts per million, or a chemical shift of 0.9. Alright, so if we move on, let's think about spin-spin coupling, or what we actually refer to as J coupling. Now when we're actually thinking of a structure, and here we've got our compound, we can see that each of the hydrogens in this molecule are equivalent. And so consequently, they would occur as one resonance in our proton NMR spectrum. Now when we step it up, and here we've got a structure of ethanol, we actually have two chemical environments. So we have HA in blue, and we have the purpley pink HX. So we all know that they actually will couple together. And we can think about them being split by the n+1 rule, which I'll give you a little bit more complex. It's the 2ni+1. If we look at the purple HX, they will be a quartet because they will be split by the 3 HAs, whereas the signal responsible for the HAs will be a triplet because it will couple with the adjacent HX. Now if we're thinking about how many bonds apart they are, we can actually see that HA, 1, 2, 3, is 3 bonds away from HX. So what we say is that HX is a quartet, and it couples to HA with 3J, or 3 bonds away coupling. HA couples with HX to give a triplet, and again it couples with 3J coupling because HA and HX are 3 bonds away. Now in terms of our NMR spectrum, we know that we've got a frequency output, and coupling constant is actually measured in Hertz. So we've got HA, which is split by HX, and they are 3 bonds away. So we see our triplet here, which actually shows 3J coupling. If we have a look at HX, HX is split by HA to be a doublet, and again 3 bonds away, so we have 3J coupling. Now on our x-axis of our NMR, we actually have it in terms of ppm, but that ppm has come about from conversion of a frequency using the known operating frequency of the machine. So now we know we've got 3J coupling, which comes about from HA coupling to HX and vice versa. But let's think of that a bit more in terms of the distance between the peaks. And so we think about this as tree diagrams. So what we do is we look at our multiplet and we work out how the coupling has come about. So if we're thinking about what's going on, if we look at HX, HX couples to HA, and it's a doublet. And we know that by the n+1 rule. But if we're thinking about how it is split by the frequency in which it couples to it. And the distance between these lines in the NMR spectrum in terms of the frequency is 5 Hertz. in a little bit we'll work out how that number comes about. Whereas for HA couples to HX, and there's two HXs, so for the first one it's actually split into a two-line pattern, and then each of those is split further by coupling to the second HX, and that produces a three-line pattern. Now if we look at how many lines come together for the outside, we've got one line there, we've got one line there, but for the middle we're actually having two lines come together, so we've got the two lines there, and that is what gives us our intensity in our triplet. So in order to determine the size of the coupling constant, we need to determine the difference between the lines in parts per million, and then times by the operating frequency of the machine. So here we have our doublet, and the chemical shift of one peak is 3.88, chemical shift of the other peak is 3.93. So the difference between these two is 0.5 ppm, and we need to times that by our operating frequency, which is 100 megahertz, in order to get the coupling constant. So if we do that calculation, we can say that the size of our coupling constant in hertz, which is the units for coupling constants, is 5 hertz. And so now if we come over to our triplet, we can see that we have a difference of 0.05 ppm between both of those. And again, we have a distance of 0.5 ppm between both of those. So here we have a 3J coupling constant also equal to 5 hertz. And that makes sense because HX will couple to HA and HA will couple back to HX. So you would expect them to have the same size coupling constant because that 3J is telling us that it's the interaction between HX and HA in a frequency context. So you'll be doing a little bit more on this in the workshop, so don't be too concerned if you don't understand this completely now. We also can see coupling through 4 bonds, and that's called 4J. So 4 bonds through 4J. So here is an example of coupling in aromatic rings, which is seen through 4J, and again we have these hydrogens which are 4 bonds apart. Now because the distance between them is further than 3 bonds, the size of the coupling constant in a frequency is also less. So these numbers are around about 0 to 3 hertz, whereas 3J is typically around about that 7 hertz number. One of the requirements to see 4J coupling is that you have some planar or sp2 nature to your molecule. And so here we can see that we've also got it through an allylic compound, so one that has these two sp2 hybridized carbons. So metacoupling is also called W coupling. And again, you can see that because we have this constrained molecule, we've got many sp2 centers on our aromatic ring, that we do have this W. So if we were to think about that in terms of a structure, here we've got HX and we've got 2 HAs. So if we're thinking about the number of bonds, we have 1, 2, 3, 4 bonds between our HX to our 2 HAs. So HX will couple to our 2 HAs and be a triplet, and HA will couple to 1 HX and be a doublet. So we can see straight away here which resonance belongs to which proton environment. And if we're thinking about drawing our tree diagrams, we always want to go back to 1. So here we have a doublet, bring it back to 1, and the coupling constant, in this case 4J, is the distance between these peaks in frequency. Likewise here with HX, we can draw our lines. We need to bring them back to 1. So I put my little hats on to bring the 3 back to 2, draw my 2 lines in, draw the 2 back. And so here we have our 4J coupling constant, each of the distances where I've written the 4J are exactly the same. And again, we work that out by knowing the chemical shift of each of these peaks and times it by the operating frequency. So this now gives you a good background to be able to do the NMR workshop for 2911.